on Thursday, we were talking about artificial gravity. We watched all those videos about, the effect of not having gravity in the International Space Station and stuff like that. Okay? But what it came down to essentially here was that if I want to have a spinning drum, like we see in most modern science fiction movies, to generate artificial gravity, the principle of that is to harness my inertia to make me push against the inside of the drum so that the drum has to create a reactive force or normal force that pushes back towards the center that feels like gravity. So when it comes right down to it, all artificial gravity comes down to this. I want the normal force on the inside of the drum to act as a centripetal force. Ideally, I want the value of this normal force to feel like what force? Gravity. Which means m times g equals mv squared over r. That's what artificial gravity comes down to. I want the force of that drum to feel like I'm at home, so I want the centripetal force to feel like gravity. Okay? And then I can manipulate for either how fast the drum needs to go, if I know what the drum's radius is, or if I know the speed of the drum, what the radius of the drum might be. Because really, those are the only two things I might be calculating for. I want g most likely to be 9.81. Okay? Everybody with me there? Right, so that's how artificial gravity questions work. So if we're looking at this question here, okay, they're telling us that they want us to calculate the speed at which a 1,700 meter drum, which is big, okay, has to move so that the astronaut feels a force on their feet equal to their Earth weight. Okay, so they're telling me this applies. Okay, Fg equals Fc. Mg equals mv squared over r. What happens to the mass? Yeah, is that important? It means that every astronaut, regardless of their mass, feels like they're at home. Yeah, that's important. Okay, so we cancel that mass off, and we're looking for v. So I multiply both sides by r, and then square root. So I'd be left with the square root of GER equals v. Okay, so g times r square rooted will give me the speed at which that station has to turn. Okay, so that would be 9.81 times 1,700 square root. All right, so we're looking at 129 meters per second. Actually, 129.1 because we would have 4 significant digits here. Is that fast?
Yes.
It's very fast. Okay? I don't know if you guys remember, but at the end of The Martian, when they're rescuing Mark Watney with that kind of semi-ridiculous maneuver they pulled, okay, they actually stopped the rotation of the habitation module. Okay, because that one guy had to go outside of the ship. Okay? If that habitation module had been rotating, and he had grabbed onto it but then lost his grip, he would have been thrown off at a very high rate, not this big, because obviously it wasn't 1,700 meters, but he would have been thrown off at a very high rate of speed. It would have been dangerous for him to be interacting with that thing, moving at the speed he would have to do that. Okay? So same would be true here. You wouldn't want to lose your grip on that, because you'd get thrown off at 130 meters per second, okay? Which is pretty fast. All right, would you notice that if you were on the inside of it? Nope, not at all. Everything around you and you are moving at the same speed. It's like being on a train. Okay, if you're on a train and you're walking, you don't really notice that the train is moving. Okay, because you're moving with the train, right? Now, you can look outside the window and feel like you're moving really fast. Okay, if you like look out the window and run on the train, you add your speed to the trains, and it looks like you're going really fast. Okay? Somebody outside the train would think you were the Flash. Or if you turned around and ran backwards, okay, what would it look like to a person outside?
You're just standing still.
Right, like the train is moving underneath you. Yeah, it would look that way, but it's not.
Sorry, this is a really dumb question. But it's like, when you jump in a train, why don't you go flying backwards? Because you're like disconnected.
Because you're
yourself from
inertia,
it.
you're inertia.
But you're not jumping forward with the train.
No, if you just jump off.
If you just jump straight up,
Yeah.
he's right.
Okay.
When I'm moving at the same speed as the train. If I jump up, I'm still moving at the same speed as the train.
Oh, okay.
Yeah?
Yeah, that makes sense.
So I have that initially. If I jumped onto the train, so there's an open door and I time it right and I jump through the door, which don't try that, okay? But if I did, that would happen. What you're imagining would happen because I would be moving perpendicular to the train, so I jump through the door and then the train would move under me until I landed.
Okay.
Yeah, so you could like enter and turn the corner in the same movement without actually having to turn. There would be other problems with that. You hit something and get hurt for sure.
Okay. Thank you.
So that's why I say don't try. Okay, so that's how our artificial gravity stuff would work for a spinning drum. Okay? All right, that's all we need to do. That was all we had to do to finish up artificial gravity. Okay, so now we're going to look at vertical circular motion. Okay, so I need you to find lesson 4.1 in your notes package on vertical circular motion. So vertical circular motion is different. Okay, everything we've looked at thus far has involved something moving with uniform circular motion. So this thing's whirling around and around and around, and its speed is constant. Okay, but as soon as I move to vertical circular motion, what happens to the speed? Slows at the top and speeds up at the bottom. Speed is no longer constant because now what's involved? Gravity's involved. Okay, so when I have vertical circular motion, gravity is suddenly a factor, and I no longer have uniform circular motion. I have non-uniform circular motion. And this can create all kinds of perceptual idiosyncrasies, we'll say, okay, for someone who might be moving in a vertical circle. Okay, so while I'm whirling this in the vertical circle, if you look at my hand, when the thing's going over the top versus when it's going in the bottom, what's happening to my hand?
You have to generate a lot more, like force to push it back quickly almost.
Exactly. Okay? When it's at the top, it's really easy for me to keep it in the circle. In fact, I don't have to do anything. It'll just stay in the circle as long as I go fast enough. Okay? But when it gets to the bottom, it's pulling down on my hand each time. Okay? So there's more force needed at the bottom than there is at the top. Okay? From me, that is. Okay? The centrifugal force is kind of the same. Okay? There's more force needed by me at the bottom because at the bottom, I not only have the inertia of the tape to contend with, but I also have the weight of the tape, the gravity, okay, pulling out. So now I have to counteract both of those forces. Where at the top, gravity works, works for me at the top. Okay? It's acting now towards the center. So I don't have to pull on the string nearly as hard because gravity will keep it in the circle for me. Okay? As long as it's moving fast enough. Okay? Everyone okay with that idea? All right. So if I go faster than I have to, okay, I still have to pull when it goes over the top, yes? Because it'll want to leave. Okay? But if I go slower, just fast enough to maintain the circle, what happens to the string at the top?
It becomes slack.
It becomes slack. Because again, I don't need to generate any centrifugal force. Gravity does it for me. Okay? Remember back in Unit 1 when we were doing projectile motion? All projectiles follow what shape?
An arc.
An arc. What does this thing become?
Basically, like a bunch of connected to each other.
Yeah, well, it's a projectile. Okay, when it's going over the top, it's a projectile. Okay, I don't need to do anything. Once it comes past horizontal, I don't have to do anything. Unless it's going really fast, then I do. Okay, the faster it goes, the harder I have to pull. But it's always less over the top, always more at the bottom. Okay, as speed increases, I have to pull harder. That's mv squared over r. Okay, but there's a point where going over the top doesn't require me to do anything. If I were that piece of tape, how would I feel going over the top?
Light, I guess, like light.
How light?
Weightless.
Yeah, I feel weightless. For just a second. You ever go over the top, go over a hill on the road that's kind of a sharp hill and you went over it kind of fast? Okay? You've never done that with the speed bump out there. Okay? Because you shouldn't, that'll rip your transmission right off. But if you go over the top of a hill fairly quickly, especially on a roller coaster or something like that, you get this feeling of your stomach and your heart and everything kind of coming up a little bit. Because they kind of are. Okay? You're strapped into the car, so your body stays put, but your internal organs have their own inertia. And you kind of move up a little bit, and you get that sensation of, whoa, okay? You get that feeling of, oh man, I just suddenly felt a lot lighter. It's because you were a little bit lighter. Okay? Not in terms of like your mass, but your weight, your apparent weight changed. As a result, your inertia wanted you to go in a straight line, but the car kept you there. Okay? And so you feel a little bit lighter. If you go over the top of a hill fast enough, could you leave the ground?
Yeah.
Yeah. Okay? You could launch yourself. Okay? Now, not that anyone would ever do this, okay? But when we first moved into this school, okay, somebody tried that on the speed bump out there. Okay? Like a little tiny hatchback with like 5 people in it. And jumped that thing. And then came crashing down. And then this big, kind of elongated, blackened shape was left behind on the road. It's called the transmission. You kind of need that, it's important. Okay, but all that weight came crashing down onto the road, the suspension couldn't handle it, you couldn't break it down, okay, like the thing just bent like a piece of celery. Okay, so yeah, it wasn't good, you wouldn't want to try that. But the people inside the car would have felt weightless, that's my point, okay, for at least an instant while going over. And then they would have hurt. Because when you come crashing down on a hard surface like the road, okay, in a tiny little car, it hurts, okay, because you feel a lot heavier. That's what's going on at the bottom. Okay, at the bottom, you feel a lot heavier, okay, because the exact opposite is going on at the bottom. At the top, there's only gravity, but at the bottom, there'd be, like if this was a roller coaster, the force of the track also pushing. Okay, pushing you towards the center, okay, and so you feel a lot heavier because that force would have to counteract your weight and your inertia, and the faster you're going, the more of that you're going to have, and so you'll feel really heavy. Where in this circle, if this was a loop on a roller coaster, where would you be the most likely to black out? Yeah, at the bottom. Okay, because at the bottom, your blood wants to go which way? Down, away from your head. Okay? And so if you're going fast, right, that's where you're gonna black out. At the top, you might be upside down, but remember, you're going with it. Okay? So unless you got stuck and you were hung upside down, which would be bad, okay, you don't have any worry at the top necessarily. But if you're going fast, could you black out in either spot?
Yeah.
Yes, but you'd still be more likely at the bottom. Okay? That's gonna be the most likely place. And anytime a fighter pilot blacks out, it's always when they're coming out of a dive, when they're doing that climb, because gravity's pulling down, the force of the airplane is pushing up, okay, and that's where they're going to be most likely to black out. Okay. All right. So understand that vertical circular motion is not uniform. Okay, demonstrated that with the ghetto physics tape and drawstring demo. Okay. Learn the forces that contribute to vertical circular motion. Gravity is going to be one of them now. Okay, it's involved. And if we're talking about something on a string, the tension in the string. If we're talking about something on a track, it would be the normal force of the track. Yeah. Okay, those are going to be the things we're going to be looking at. Okay, and understand that for vertical circular motion, Fc equals forces in minus forces out. Okay, that's really important. Remember on the first day of this unit, I said that Fc was like net force. Right? It was mass times acceleration. And it was also then the vector sum of all forces, which is why we can say that for a vertical circle, Fc equals forces in minus forces out. There has to be a net force in, or this object doesn't stay in the circle, agreed? Okay, so that's why we can say this is still the vector sum of all forces. If I subtract the forces acting out, from the forces acting in, whatever's left is my centripetal force, my net force acting back towards the center of the circle. Okay? The only forces we're going to be dealing with here are gravity and normal force, or gravity and tension. Those are the only situations we're going to have. Okay, has anyone ever seen somebody do the bucket, the vertical bucket full of water trick?
Oh, yeah.
Okay, I used to do it, but we don't ever get buckets that are strong enough to handle it anymore. They stopped making ice cream pails with metal handles. They switched to plastic, which switched to me putting a bucket of water into the whiteboard over there. Okay, so don't do that demo anymore, because, well, it's dangerous. People could get hurt / wet. Okay, so we don't do that anymore. But, okay, I could whirl a bucket of water around and around in a circle like this and not get wet as long as I move it. Well, it won't be a constant velocity, as long as I move it fast enough. Yeah, at a minimum speed, at a minimum velocity, okay? Because if I don't move it fast enough, I just go like this. I'm gonna get it to here and it's gonna dump on it, okay? I've gotta get it going so that there's enough inertia to pin the water to the bottom of the bucket and hold it there. Okay, that's the minimum speed required to achieve vertical circular motion. Okay, without that, you fall back in. Okay, and so that's tricky. Is minimum speed fairly fast then for all reasonable sized circles? It is. Okay, here's what can happen if you don't achieve minimum speed. I mean, they figured it out, right? Like they didn't have enough speed to maintain, they didn't have the minimum speed required, so they understood, we need more energy. So they got some elastic potential energy to add to their gravitational potential energy by hooking up a bungee cord to a truck. Because, well, reasons. Okay? Probably made sense. You know, nothing bad could possibly happen. Probably. Okay? So they got it figured out and they got to that minimum speed. Okay? It's tricky, okay, getting to that minimum speed. Okay, so yeah, it's possible to do that, but you've got to maintain or attain this minimum speed going over the top of the circle. Because as he was running over the top of the circle, when he got to here, gravity is pulling him back towards the center. Okay, and you can see that he barely was able to exert any force on the top of the circle when he ran. That's what I said, like, look, his leg is already straight. Okay? When he pointed his toe just to make contact with the top of the circle, right? So he was falling. He was falling because of gravity, but he had this path. He had this projectile arc that he was already following and had enough speed that as he followed that arc, he was able to reconnect with the track and run out the loop. Okay? But at the top, the only thing acting as a centripetal force was gravity. If he'd been able to run even faster, he would have pushed on the track, and the track would have pushed back, and we would have added some additional normal force. Okay? Would he have felt a little heavier then? Because when he ran it, according to what we saw in the video, he would have felt weightless going under the top. Okay, that's why he wasn't able to push. If he was able to run a little bit faster, he would have pushed, and he would have felt a little bit of weight. He'd have still felt lighter than normal, but he'd have felt a little bit of weight. Okay? Down here at the bottom, when he completes that loop, the normal force is lots bigger, because which way is gravity acting?
Down.
Down, which is out of the circle. Okay? So gravity doesn't switch direction. It's always down. But in terms of the circle, it's sometimes into the circle and sometimes out of the circle. Okay? Everyone okay with that? At the top of the circle, it's in. But at the bottom of the circle, it's out. Right? So what we always have to be able to do is kind of do a free body diagram for these different positions in the circle. Now, this is the hard way to do it. What if you ran over the top of the circle?
With this pushing force of gravity, you'd be moving faster than that. You'd be getting pulled down more because he's pushing at the top too, going down.
Okay, he'd be pushing at the top. Which way would normal force act if he was running over the top?
Upwards,
Upwards. Which way would gravity act?
down.
Downwards. Gravity always acts down, so gravity always acts into the center at the top of the circle. But if you're on the outside of it, okay, you don't feel weightless unless you're going fast enough. That's what we were talking about at the beginning of class, where you kind of went over that hill and you felt like everything inside of you was moving up, okay? If you go fast enough over the top of that circle, you'll feel weightless. That's how NASA's Vomit Comet works, okay? The zero gravity trainer we were talking about the other day, okay? When we were watching that part of 2001: A Space Odyssey where the guy was weightless in the space plane, okay? That was filmed inside the Vomit Comet. All of Apollo 13 zero gravity scenes, same thing, okay? Filmed in that so that 30 seconds at a time, they could get this sensation of weightlessness. Because if they go fast enough over the top of that circle, the normal force disappears and you feel weightless. If I'm just standing on the top of a circle, the normal force and the force of gravity are equal. But as soon as I start running or moving, I get inertia that wants me to go that way, okay? Which takes away some of that normal force that I would feel, and I feel a little bit lighter every time I go over the top. Okay, so if you try to do that loop-the-loop, which is what we just saw, okay, you're going around the loop like this, okay, and you're trying to go fast enough that you don't fall back in and achieve that minimum speed. So, if I'm going just fast enough to stay in that circle, we said that gravity was the only force. So, if I knew the radius of the circle, could I calculate what the minimum speed for that circle would be? I could. Okay, I just plug in whatever my radius value was for r and solve for v, because what would happen to m? It would cancel. The minimum speed of a circle is not dependent on the mass of the person in it. It's dependent on the radius of the circle and gravity. So if we're looking at how a vertical circle sets up in terms of forces, this is what I was diagramming before. At the bottom of a vertical circle, gravity pulls down. Normal force, or if it's a string, the tension in the string pulls back. And here at the bottom, that normal force is large because it's not just gravity, it's also your inertia that it's working against. Okay? We don't ever do any problems to do with the sides of a vertical circle because the side of a vertical circle, gravity is perpendicular to the circle and plays no part. So that's your centripetal force, whatever the normal force or tension is on the sides. Okay? At the top, on the inside, gravity pulls in, and if you're going faster than you have to, normal force pushes in as well. Okay? If I'm going over the top, then normal force pushes out, and gravity pulls in. Agree with me there? Okay. So, so the only three positions we're going to look at are the bottom of the circle on the inside, top of the circle on the inside, and top of the circle on the outside. Why will we not look at the bottom of the circle on the outside? Yeah, you'll fall off. You can't go under the bottom of a vertical circle on a track. Okay? Well, actually, you could, but you'd die. Okay? And that's also why fighter pilots never go inverted at the bottom of a vertical circle. Okay? Think about where your blood goes. If I'm on the bottom of this vertical circle like this, I'm already upside down. Which way does my blood want to go? To my brain. So gravity pulls my blood to my brain. My inertia makes my blood want to go to my brain. Everything makes my blood want to go to my brain. That's the opposite of blacking out. Blacking out is when the blood wants to go away from the brain. What would happen to my brain if all of a sudden all the blood in my body wanted to go there and went there?
Why not?
Red eye. That's what they call it. Okay? That's a negative g-force. Okay? Positive g-force means you feel heavier than normal. A negative g-force means things are working backwards. If all the blood in my body rushes to my brain, the little tiny delicate blood vessels in my brain that are totally not designed to withstand that will rupture. Okay? It would essentially be like having a massive stroke. Okay, like all the blood vessels in your eyes would burst. Have you ever seen what it looks like when someone like has a bunch of blood vessels in their eyes? It looks really creepy. Okay, that would happen. Okay, all the blood vessels in your eyes and in your brain, and it would be a massive aneurysm. Okay, and it would kill you. The human body can withstand massive amounts of positive G-force. It can withstand very little negative G-force. Okay, having all that blood go to your brain can be lethal pretty quick. Okay, so we got to achieve a minimum speed to stay in the loop. Like Homer. Has anyone ever seen a Simpsons movie?
No.
Homer does the ball of death. Okay? All right, so as we were saying, that your perception of things as you go around this circle is going to change. That is your perception of your weight. Okay? If you recall, back in Unit 2, I told you that sometimes we call normal force apparent weight. Okay? That's going to be important because that term comes up all the time in this unit. So if it says calculate the apparent weight, you're looking for the normal force. Because we don't actually ever feel our weight. We feel the normal force, which can change depending on our position or condition. Okay? That is, if we're moving in a circle, it can change. Okay, so apparent weight is your normal force, and you can sometimes feel apparently quite heavy, apparently a lot heavier than normal, and apparently lighter than normal, and apparently weightless. So if you are experiencing a condition of apparent weightlessness, are you actually weightless?
No.
No, you still have weight. Your force of gravity would still be m times g, right? But you don't feel it because you're moving and doing something that makes you feel like you don't have any weight. Okay? Even on the International Space Station, they aren't weightless. They are apparently weightless because they're always falling.
They're just moving in a
They're just
circle
moving in a
fast.
circle fast enough that they don't get any closer to the Earth. That's how satellite motion is achieved, which is the next thing we're going to talk about. Okay, but not today. So your apparent weight can change. So I'm going to show you this video. This is actually, if you get a chance, Cirque du Soleil Cruza is coming back to Calgary. Okay, this video is now quite old. Mr. Dickey went and saw it like way back when it came, and they have this thing called the Wheel of Death. Okay, and it's a double spinning wheel. So there's two like wheels, and the whole thing spins, right? And they put a person in each wheel, and these people just run. Okay, and they can make this thing, and they do all kinds of the crazy, like Cirque du Soleil stuff that always happens in Cirque du Soleil. But you can really see all this vertical circular motion stuff we've been talking about. The points where they're apparently weightless, the points where they're quite heavy, how speed affects how they feel. When it's rotating slowly, they look a lot different than when it's rotating quickly. Okay, when they're close to the center versus not close to the center. Right, all of that kind of stuff. So I'm going to show you that just because we could see then though pretty clearly that their weight did change, or their apparent weight changed as they were going around the circle. Now, as we were saying, NASA has this zero gravity trainer that they use where they create a situation of apparent weightlessness as they go over. Okay? It's way better than working inside the big water tank, because even in a water tank, you still have weight. And you've got buoyancy working for you, but you still have weight. So it's not quite the same as actually putting people in this plane and having them do this stuff, okay, and figure out how it's going to make them feel, okay, how do other things behave in zero gravity, and kind of getting used to that. Okay? So we can create that situation or feeling of apparent weightlessness as we go over the top. All right, so this is apparently a real track. So have you ever played with those orange Hot Wheel tracks when you were a kid?
Yeah.
They got the real thing for real cars.
That was my childhood.
Okay? So you got to go fast, and your car will stay in it. I would imagine there's a pretty good waiver for this before you get in it. Okay? But you can do that as long as you get going fast enough and keep that minimum speed. Right? So all we have to remember here is that at the different points in the circle, centripetal force always equals the same thing. The force is in minus the force is out. Okay? So if we're in a situation where normal force is acting in and gravity is acting out, that would be the bottom of the circle. Okay? If we're at the top on the inside, both normal force and gravity act in, and there are no forces out. And then if we're on the outside, gravity would act in, and normal force would act out. Okay? Until you got going fast enough that your normal force became zero, and then you would feel weightless, which is what they do in this next video. I mean, you can see, like, there's lots of stuff that goes into something like that, but, yeah, so for our vertical circular motion stuff, okay, the big thing to remember here is that centripetal force is still net force. So it's still the vector sum of all forces, which is why the whole forces in minus forces out thing works, okay, because we're still doing the vector sum of all forces when we do that. Okay, so going forward here, guys, we'll look at a few kind of simple problems like this one. Okay, so let's say I want to calculate the minimum speed required for this roller coaster to stay on this track if the radius of that loop is 9 meters. Okay, now obviously roller coasters are not built so that they rely on the speed of the roller coaster to keep them in the loop. Okay, they're not built that way. There's a set of wheels on each side of the pipe that makes up the track so the roller coaster can't fall. Okay, but if we were saying that this is a roller coaster that would rely on that, okay, all we know is this. They give us the radius, and we have to assume that this is where?
On Earth.
On Earth. Okay, so G. There's only a minimum speed on what part of the circle? The top, on the inside or the outside? Inside, because you can't fall off the outside, okay? And there's no minimum speed for the bottom because you can't fall out of that either. So we know then that we're dealing with the top of the circle where gravity acts in, and so does normal force, except that if we're only going fast enough, we would feel what? Weightless. So there is no normal force. So we're saying that the force of gravity is the force in. There are no forces out. So that means that Fc equals forces in minus forces out. There aren't any. So that means mv squared over r equals m times g. Can I calculate the minimum speed for this roller coaster? Okay, so what happens to the masses? They cancel each other out. Okay, I multiply both sides by r and square root. So v would equal the square root of 9.81 times 9. So we're going to be looking at something around 9.2 or so. Okay? So, well, we got a square root of it. So second function of 9.81 times 9. So 9.4. Okay? So this roller coaster has to go at 9.4 meters per second in order to stay in the circle of its own accord. Okay? All right, we will leave it at that for today, and we'll be looking at some more vertical circular motion stuff tomorrow after the quiz. Okay, I'll post that later on.